I have this code and this is the result. It should be actually like I track, this is the code that I have, this is the data went to this code, this is the result that's generated, this is the performance that I received, and so on and so on. Why do we want that? We want to have a way that if in the future you want to compare, like it says that I have this version of the model and I want to see that why it did better than the previous version, or why it did better than the one that we had 6 months ago for other customers. Then if you don't have this basically stored, this information, then you're going to have hard time in comparison. You need to start looking through all these Jupyter files, which, it's like, it's not fun. So why we want to do experiment tracking? Let me zoom in. Why we want to do experiment tracking? First, ML projects have far more branching and experimentation. So if you think about like a software, in software we could do code tracking, and by far having a GitHub, that's just kind of enough, right? Because it tracks everything for you. But when it comes to ML models, code is just one component of that. A small change of the data, it could have a drastic change on the output. So it's like and all of you have done, even myself, when you basically build something and you have all these Jupyter files and every one of those basically contains something, right? So you want to be sure that, you can track all of those. The other thing is that debugging ML is difficult and time consuming. Most of the time, things are not straightforward in machine learning, right? You try to put pieces together to build a model, and it's really hard to debug that. Running experiment can be time consuming and expensive. And that's another thing. It's like, if every time you want to start an experiment, if you don't have an idea in mind, you basically might go through same process then next month when you start a new project until you get to a certain point. Like it's kind of like there's a cold start for every project that you might go through all of this, right? And then there is a certain, more like a detailed task that you do for the current modeling that you're doing. So what if we could have these experiments to be less expensive and less time consuming? What if we could automate series of basically components of this experiment? That means if next time I want to start a project, before doing anything, I have this basically let's say agent, or whatever you want to call it these days, that runs and gives me all the necessary early basically definition that I need for the project, and then I continue from that point. So instead of you try to make all these connections, call to database, get the data, and you try to figure out how you want to do that. What if you have all of those ready? So, and what does it mean to track experiments? Basically, so the first thing is that, well, when you track an experiment, it enables you to duplicate the result. What does that mean? So you run a model, and lots of them, especially in machine learning models, they have a local basically convergence instead of global, right? That means when you run it, if the next time you run it again, you get a different results, right? And how could you duplicate that? What if you like that result and you want to basically see that if you can basically replicate that? So you need series of basically metadata, like information, system information, in order to be sure that you get the same answer.
So I was just thinking, is it like adding a seed to a model?
That's just one component of it, that's correct. But it could be so many components. It's just even a simple update for a library version change could give you a different result. Right? Seed is one of those. It enables you to compare the experiments. It helps you with manage data on code version, hyperparameters, metrics. It helps you basically to organize them in some a repository, and basically also it's make them available to everyone else. So imagine now, every time that in your team, there's a team of ML engineers, data scientists, and everyone is working on a project, and maybe there's one project that's shared across every 4 or 5 engineers, and the team lead wants once in a week or twice a week to have a way to look at the result across all this project and do a comparison, right? Right now, the way that it happens, most of the companies is manually. You basically schedule a call with the team, you go say, hey, demo me what you have, you ask questions and stuff like that. What if you had this central basically API that when you go through that API, you see everything, you see all the runs that they had, you can basically, without a need to have the basically data team or basically engineers team, because all the metadata is out there. You can basically see what was the model, what was the hyperparameter, what was the result, what was the data, and so on. So that also basically this experiment tracking that also provides you. Now, they are, the reality is that the Jupyter Notebook, Jupyter Notebook, Jupyter Lab is really a strong tool. All of us will love that. The problem with Jupyter is that, well, it's not for production, okay? And one of the problem in industry is that when you work with data science teams, when you want to deliver the result to the ML team to basically productionize the code, they give you a Jupyter file. And that's the reality of that, The problem with Jupyter file is that it's whatever runs in Jupyter doesn't mean it will run outside of the Jupyter, okay? Because, it's just all those like a cached and stuff that your Jupyter has. And they might even still some libraries that you install via Conda, maybe it doesn't install via pip and stuff like that, right? So the thing is that there are some tools that you can use to ensure that your Jupyter basically code, whatever you have in Jupyter, can be converted to Python and you can basically run it. One of them is NB-convert, basically convert Jupyter to Py. You have NBDim is like for diffing, similar to when you do diffing across .py code, you can compare it to Jupyter file basically. Jupytex basically helps you with versioning and basic conversion on the Jupyter files. There's this Neptune notebook basically has all of this together. But then also, if you want to do some sort of like a smoke testing that means that before I deliver this, like I have this Jupyter file and I convert it to a Python, and I want to see that before I pass this to the engineer team, can they run it by itself? So that's called the smoke test. So you can basically do this, something like this. Can it run or not? Most of the time, no. The output of the Jupyter doesn't run. It depends on also how you code it. The problem with Jupyter is that, and I highly recommend you don't upload your Jupyters like that. It's when you go over Jupyters, it's like all the printouts and everything is in the Jupyter, right? So it's not code actually, it's just basically a notebook technically, right? So that's why, it's despite the fact Jupyter is pretty strong, it's necessary for day-to-day work, it's not the correct source for the delivering code basically. Now, then we're all aware of Git basically. And I don't think that we need to talk about much about that, but let's go here. Now, tracking runtime parameters. So there are a series of things that you want to basically track also as part of the experiment. If there is any config files, basically, you have this config files and it has address to the data that you need. It has some information for the model that if you need to run the model, these are basically maybe the parameters that you need to pass to the model, and also a command line that how you can run this model, right? So that becomes as part of the experiment. But I think you all have worked with ML flows so far, right? Correct? We had lab on ML flows. And if you see an ML flow, when you do experiment, after that you save, when you go to the part that shows the artifacts, it also gives you code how to run the artifact, right? So that's why that makes MLflow is a really great tool for experiment tracking, because everyone can basically go look at the model that you ran, they can run it, they can deploy it, and so on. You can compare them against each other, right? So that's just keeps in mind. And then it's just an example. If you have any runtime parameters, you can just use on parts basically to run that. Now, we're going to just quickly talk about some of the tools that are out there for experiment tracking. Well, the first one we're going to quickly go over is like a data versioning. So the thing about data, we know that data reflects the word and the word will change. So, you just need to have a way to basically track that. Experimental change include changes in the data. Most of the time, when you do experiment, you change data, you add features, you remove features, and so on. And then tracking, understanding, and comparing basically these duplicate experiments requires having access to that data. So you basically need to track this data. So that becomes a one component for your data versioning. That means which version of the data are used for this specific experiment. And if you have also already have something like DVC or Git large file system that for that version, where is that data stored? Or how I can replicate that version of the data, basically. So these are some tools for data versioning. Neptune, Python, DVC, ML metadata. So these are all basically different tools that you can use for data versioning. And this is just an experiment for comparison, which you have seen similarity to this in MLflow. There is another one also, it's kind of like a tensor board. I don't know, has anyone here worked with tensor board before? Yeah, okay. So tensor board, it's a library by TensorFlow that if you, especially for the TensorFlow models, it basically allows you to do this comparison across different models, basically. And also look within the model itself to understand the layers, the weights, the parameters, and stuff like that. So now, when it comes to the model development, so we want to be sure that we organize this process. That means we need to be sure that we have a way to search through our experiments. Not that you need to necessarily use MLflow, but as long as you have a place that you have stored the necessary metadata that you created, and you have a way to load or search through that metadata and, I don't know, create a dashboard over it, then that does work for it. That does the same thing that MLflow does, basically. So that's your call. Basically, your goal is that to be sure that you can all those metadata organize into something digestible, something that you can basically read, or someone without the really technical knowledge, they can basically look at. And then helps you to make your data shareable and accessible by others, basically. That's also similar to the MLflow, which we saw before. And if you wanted to work, if you're working with Vertex AI and you want to use Tensor board over there, I think it's called Vertex Tensor board. So that's basically the same thing as a function that you can use. Now, the rule here to remember is that similar to everything we have seen so far, experiment tracking is also iterative process. So it's not doing once only. You basically create iteration for your ML model. You need to be sure that you have, for every experiment that you start, you also have a baseline. You have, like, you start the experiment with a baseline. This is the baseline. We keep adding new models, new approach, new basically run, and we compare it with this baseline. Okay, so that becomes like an approach for you. You need to be sure that you can develop and implement and evaluate and get those metrics, basically. And then I think the last one is more important: latency, cost, fairness, and etc. And what you want to be sure is that not only that you develop code and you basically track this experiment, you also want to be sure that you monitor for latency, for throughput, and stuff like that. Model, and again, at the end, you cannot use it because it's too slow or it's too expensive. So have a way to also monitor for those metrics. And here it talks about fairness and bias. We will talk about for more in details, but I think as part of your project, if it's applicable, you need to also basically monitor for that. Now we're going to talk about MLOps in industry and levels of MLOps that exist out there, okay? So, but we're going to first start with the difference between data science and software engineers, basically. Well, data scientists, let's start with that. You often work on a fixed data set, a snapshot data. So you download the data and you just do work on that data, okay? you focus on model metrics. You have this fixed data set, you focus basically on, I want to reach this accuracy. So you keep trying different models, trying different basically manipulation until you get to what you want. Your prototyping again happens in Jupyter Notebook. Data science are expert in modeling techniques, feature engineering. And most of the time, what is being ignored by data science team is the model size, cost, latency, fairness, and all those metrics, right? So because the focus is not technically around how you can run it, the focus is that I want a model that gives this accuracy. I want a model that gives F1 score, for example. On the other end, when it comes to software engineers, basically, the goal is that they want to build a product. They're highly concerned about the cost, performance, stability, schedule. Basically, they want to be sure that this is like a scalable product overall. They want to identify the quality through customer satisfaction. They want to basically be sure that they can detect, handle error, and stuff like that. You need to account for the security concerns that you have, or basically safety. And overall, basically, how you can have a piece of product or a product that can basically live for a long time, you know. That's the focus that we have over there. Now, there is a growing need for ML in this basically in this field right now. And the problem is that, well, we have large data sets. We have technically kind of like inexpensive on-demand computer resources. One of the challenging things that we deal with is that the ML, especially these days, is rapidly growing, right? So lots of new tools comes out, lots of new algorithms comes out, and it's kind of hard to keep up, you know? And companies, they all want to invest in the ML because, you know, it's just everyone is kind of like, we want to use ML, we want to use AI, you know, especially because all these new tools and ideas are out there. So there's a growing need for ML in product and in services. And we can basically compare this problem that right now ML has with the problem that software basically had in basically 90s. So back then in 90s, software was kind of like a silo. It's kind of like not that popular. There was not a proper basically CI/CD or version control. And that's basically, it was really hard to ship software because that process, the CI/CD part was really helpful, but they didn't have it. So it was really difficult. ML right now is kind of in that region. You know, it's getting better these days, depending on companies, but lots of companies, when you actually go look at the ML, it's pretty bad. It's not ML technique. It's kind of like a really manual process technique. Now, so in today's perspective, models most of the time blocked before deployment. There's always a slow to market, and then there's always we do manual tracking, no reproducibility or provenance. There's inefficient collaboration, and of course, unmonitored models. You just deploy the model. Most of the time, it's not. We don't even think about monitoring the models until there is some fire in the house, or basically there are some complaints about customers, and like, oh, let's look at. Okay, so that is the reality right now. We have again lots of companies that are getting better. They're hiring more for MLOps. Basically, they try to address series of this, but it still is not that acceptable in industry. Lots of time companies like that. We will get there later. We will basically handle that later. You know, so now. How we can bridge the ML and IT basically with the MLOps. We talked about this before, but let's just briefly go over it again. Start with continuous integration. Well, we want to be sure that in part of continuous integration, you have proper testing, validating the code, components, and basically packaging the code. Then you go to continuous delivery. It's just like, oh, I have this package now. What can I do with it? Let me test it on for the environment that I'm targeting to deploy there. First, let me test it, then let me also monitor to performance, like a system performance. And if it's good, then I deliver it. But then we introduced the new two things, basically continuous training and continuous monitoring. And as continuous training, we want to be sure that the ML models, or basically ML pipelines, are always basically capable of training themselves. Basically, they can retrain, they can basically adjust to new data that they are basically receiving, or they can retrain based on if there are some decaying in model performance, basically. And continuous monitoring basically is a way for us to manage, basically to monitor and to detect if there is any data drift, there's any data shift, model decay, or any change in, I don't know, like the environment overall. That's basically how you can do that, the continuous monitoring. Okay, so that becomes the next thing that become important for us. Now, so if you want to look at this life cycle, so experimentation and development, as normally is data scientists, ML engineers. It comes to continuous training and so continuous training, ML engineering focus, this becomes first, and then data scientists. Comes to model deployment, ML engineering, DevOps engineers, goes to continuous monitoring, ML engineers, DevOps engineers. So what does that tell you here? That when that's why lots of companies, when you look at the job description for ML engineers, technically they want everything, right? Because you basically tap into every piece here. You need to have some knowledge over all of those, so you can basically contribute. If you have data scientists, you do it more this side. If you're DevOps, you do it more that side. But if you're doing basically MLOps, basically, or ML engineers, you do basically across all four. Okay, so just that's one of the reasons we basically try to learn so many tools. Okay, so now we want to also be sure that we can standardize the ML process. So that means we work with the ML lifecycle management, model versioning, model monitoring, model governance, security, discovery. All of this, we want to be sure that somehow we can standardize those across basically industry. So any questions so far before I continue? Right. So now we're going to talk about some MLOps methodology. It's not like that this is like actually the only methodology for MLOps, but this is just one of those, okay? So let's start with MLOps level 0. Now, so we're going to talk about, there's this term maturity, like what's your MLOps maturity, Bruce? What's your ML maturity? You can ask any company, and depending on how they do the process, you can basically give them some a score, you know? Now, basically the definition becomes the level of automation of ML pipeline that determines the maturity of the basically MLOps process. So the last time is really important. Our goal is to automate the training and deployment of the ML models into basically software ecosystem. So let's start with MLOps level 0, the manual process, which most of us we do that on at least day-to-day job for on your project or on basically whenever you have a code on your machine, you try to test things. You try to iterate quickly through them. It's always something like that. So there's a local data, and you do some EDA, and you do data preparation, you do some model evaluation, you get a feedback, you loop through here on your local machine, right? So that's the MLOps level 0. Then if you look at the same thing, now let's say, like I think my previous company, when I started work, basically we were kind of like this. It was like we were building the everything locally, and then a small team. And then we were done with the model. We have this train model. We dump it into a bucket or something, version it. And then we had ours basically, let's say, software team that they would pick that model and load it in the product, basically, you know. And so that's MLOps level 0. Everything is a manual process. So here, when you train the model, when you deploy it, most of the time you reach out to the other team and says, hey, I pushed a new model, for example. It's kind of like a manual process. So here is, again, just it's process, basically, there's the disconnection. But the also here is that, well, normally in this level of this MLOps level 0, you don't have much frequent updates, right? It's kind of like once in a while you develop a new model and you send it. So there's also no CI/CD pipeline here. It's kind of like everything manual and happens less frequent. Okay, and then again, lack of active performance monitoring. What does that mean? When you deploy the model, there's no monitoring pipeline here. So you just deployed it, and again, you just wait for feedback and or wherever there you feel like there's a complaint that, hey, this model doesn't work. So again, challenges for MLOps level 0. Well, we need to actively monitor the model performance. Well, we don't do that. You cannot retrain basically your model with the new data. And it's basically this continuous experiment. It's kind of like harder also because again, what happens is that everything is kind of a manual process. Now we go to MLOps level 1 and level 2. And level 1 is basically you have a certain level of automation in the pipeline. And that could basically come around so let's say you as an engineer on your local machine, whenever you working on the development and you using let's say DAG and create this pipeline for the modeling, the data ingestion, model training, models storing, and so on, right? And you basically orchestrate that basically. So that becomes level 1. So you just have this DAG that automates this process for you. And whatever the result of this, not the model, the code, basically goes to your source repository, maybe your code repository or GitHub that you have. So the benefit of something like this is that, well, you can do rapid experimentation. What does that mean? That you have this orchestrated things that you can easily change pieces, update something and let it run instead of manually try to basically put those pieces together. Now, the same thing when we want to look at it in a basically bigger picture. So on top, you have this orchestration basically experiment. So let's basically start here. So on the left, you do data analysis. You have the orchestration experiment, and then basically, you have some source code that goes to your source repository, Git repository, for example. And from your Git repository, basically the code comes here. Let's say this is your cloud function. So this is technically the same code. From Git repository, that code basically goes here. Then here, basically, as part of the automation pipeline. So that part, the orchestration experiment, that's where in the lab you develop something. After you develop something and you have that basically pipeline ready, you deploy the pipeline. The pipeline comes here, goes basically on some cloud service, for example. Creates a model, validate the model, saves the model in the registry. You basically do it, so this basically continuous delivery, right? So you deliver that model to prediction service and you monitor for performance. And if the performance is bad, you basically trigger the same pipeline again and you continue the loop. So you only basically added one thing. So you use like this automation pipeline plus a monitoring. Or technically two things actually. So that becomes kind of like a level 1. Why this is level 1, what's missing here? We still don't have CI/CDs, for example, here. Right? It's just kind of like you have this orchestration experiment, which, this could be done, this part itself could be manual, basically. It means whenever you have a data let's say that you package that code and it's like a Docker file and you go manually on GCP and load that Docker file on a certain service and let it run. Now, so that becomes basically the reusable, composable, and shareable component. And you have the continuous delivery here, but we don't have the continuous integration, packaging basically. You have data validation. Well, basically over there, if you see also here, you do data validation, which we have seen in the lab before what it means just to compare data for a schema, statistics, and compare to the training data. And if something, you basically trigger a warning. You do have model validation. That means that every time you develop the model, you evaluate the model, and then you need to validate it. Example of validation could be, will this model, I have a good model, the evaluation was good, but will it run in this environment? Right? Or will it basically, can I run it all of a sudden, for example, if my customer, they only have GPU with 4 gigabytes of memory, can I basically run that model, for example, over there? Can I load it and without any issues? That could be model validation, like something like an infra basically validation. Then you also had this feature store, which helps you in the process of certain features that we don't want to create them. You already pre-populate those and basically store them somewhere, so that becomes the feature store. So, and then actually here on the bottom here, you have metadata store, which we talked about it before, but it's like all this pipeline that will create artifacts and metadatas. And you need to also be sure that you have a place to store those. So metadata store is a good place basically to do that. And then metadata DB is your choice what you use for it. There are, of course, there are certain choices that are better than, but not necessarily for your project, if you want to do something cheap, you can just use a bucket and just store it also there. So now this goes to MLOPs, basically level 2. And here is where basically we are adding the CI/CD pipeline for the automation. So use that, we just ordered that image this is the same thing over there. We just made it a smaller orchestration experiment. So you have that orchestration experiment, which is technically this one. The source code goes to your GitHub, Git repository. Then you have a CI, which what it does, it gets the code, it builds it, tests it, package it. And that package goes to a CD, deploys that package, and that package deployed comes to your wherever it is that you're hosting your infrastructure, runs the basically automated pipeline. Automated pipeline runs, it gets the data, does the same thing, develop a model, train it, basically deploy the model, serve the model, monitors for performance, trigger, and so on. So that basically becomes like a level 2. There's also here this line, if you can see here from performance monitoring, all the one to the left goes back to data analytics. That what it means is that there is a chance that after you deploy, based on the feedback that you receive, you're like, we need to redo. We need to go back and basically change things because it didn't work. If we tested, customers are not liking it. It doesn't work, we cannot tweak it. So basically you go back, you do some changes in the code, in the data processing that you do, and so on. So putting it all together, start from top left, experimentation. Experimentation basically gives you code. The code goes to your code repository, but as part of experimentation, you need code and configurations. You have training CI/CD. The training CI/CD creates basically artifacts. It goes to your artifact repository. It goes basically to continuous training. Continuous training, it will be connected to a model repository because it trains and develops a model. That trained model will go to continuous model, basically deployment. You deploy the model. So here you have CI/CD also for model. Why? Because the CI part basically could be sure that we have everything. We have done unit tests and anything around this model. This model is a good model. Let's ship it, obviously package it and ship it. This CD part, basically what could do is I have this model and I have this targeted environment. Like I have a model and I want to be sure it run on a Windows, it run on a Mac, it run on Ubuntu. Basically, that comes to the CD part. You do it last minute basically test to see that it can run all those infrastructures, and then you serve the model basically. And when you serve the model, you have all these logs that comes to serving logs, and all of this will connect to one ML metadata store basically. A place that is like a centralized repository for you that you put all those basically metadata in a way that you can basically query against those metadata. You can search through those metadata also. Yes.
I not hear about the model packages to the production pipeline. The previous slide. Those packages to the production.
Yes. So think about so as part of your CI, code comes and you basically do unit tests and stuff like normally what you do in CI. Now, what if you have series of like rules that whenever the code comes, code need to goes through this additional infrastructure result. So you have a code change comes, And you break down that code, this is just an example, right? You break down that code into maybe three pieces. One piece is that this part of the code will run on Kubernetes. This part of the code will run here, and this part of the code is just a Docker I will push it. So that those MLOps packages is just what it means. Of MLOps, just how you basically package your code to ship, to deliver basically.
So you use that for the next automated pipeline, each of those packages.
Yeah, so the deployment, it gets different packages and it deploy them based on where they're supposed to go. Okay, so it's like your CI as part of your, let's say, Git actions, that CI that you have, it does series of tests and there are different results from that. They're not all together, and based on each result, the CD will pass it to a different location.
In the previous level, it was just that you were rebuilding the code again in the automated.
Yeah, so in the previous part, we didn't have those MLOps and CI. We just get this code. We brought the code, basically, maybe a Docker, large Docker file or whatever, however you have that code, and you just brought it to some cloud infrastructure and you use it. Here, you basically break this down into different components. Every component will be delivered to a different location, basically. So now, okay, so let's go back in the MLOps methodology. This one is, so this is just overall for the, actually this is just overall for TFX. We're going to have a lab today on that, but just, again, we have seen before, the TFX is just a library by Google that brings all those components, the other libraries on TensorFlow and TensorFlow related, package them together. So it becomes a productionized, basically, ML library. Don't need to spend much time on here. We have seen this before, that there are some three components here: driver, executor, publisher, and that's the metadata store. Normally the driver and publisher are fixed. You don't change that code. So the driver is responsible to read from metadata store, read the metadata, and whatever is necessary, that pass it to the executor. Executor is your code, whatever you are doing. The result that executor will generate as a metadata need to push to metadata store, and publisher does that job for you. So in TFX, these three components, the one that the executor is the one that you change normally. The other two normally are fixed. You don't manipulate those out. So this is just an example. You have the lab for it, but you also could basically use the containerized based, basically, deployment on TFX. That means that if you have a TFX and you want your TFX to load, for example, a Docker file, you can also do that. So I'm just going to skip through this. The labs are out there already. Don't need that. All right. So now let's say what we talked so far is that you do experiment tracking. You basically have a proper way of run experiment, build models, and basically save those models with the metadata. So the next thing we want to talk about is like basically model versioning. Well, that should be also part of the experiment tracking, that whenever you build a new model, how to version that model. Okay, so if you want to just quickly say that why we want to version models, think about this. Like, there are different teams that are working on basically building a model and something, and that model goes to a server, and you need to have a version for it. And what do we need? First, why do we need version, and what do we add in this version, basically? So when it comes to ML model, you need to keep in mind three things. Code itself has part of this versioning, the data that was used, and the configuration that you need in order to run, basically. So you need to package all of those, consider all of those in order to version your model. Now, when it comes to versioning of like ML models, first thing is that there is no rule of thumb here. It's kind of like a however you feel is more suitable for your company. It's kind of, we don't have a standard way of ML versioning. In software, normally we do measure, minor, patch. So normally when you install in software, you see there are three numbers, right? So X dot X dot X, something like that. So the first one, the one on the left, is the measure, is whenever you do some basically changes that is incompatible, like it's like a really major changes basically. The minor, or the second one, is when you do some change or add some functionality, but it's still backward compatible. That means that it doesn't break something. I just added something new. It doesn't break the pipeline. That becomes the minor. The patch, on the other end, is anytime we fix bugs, basically. So there's a new bug and they fix the bugs, and the next version that comes out, we see the last number is bumped up, basically. So that's how you can kind of understand what was the changes when it was software, depending on which one of these has changed. If it's the last one, is only bug. If it's the second one, that means they add some new functionality, is not going to break your code. If it's the first one, there's a chance that your code won't work on it. Okay, so that's why, for example, if you think about TensorFlow, Pandas, NumPy, when they go from 2 to 3 and so on, the version, the previous, like you cannot use the code that was built for the previous version, like if the major change you have, with the current major basically version. It's kind of normally incompatible. And again, for ML models right now, we don't have any standard basically versioning. There are a couple of recommendation or proposal basically. One of them, this one is like a major, minor pipeline. Major basically says that if there's any incompatible data or target change, that means, you see, in ML, data is a first-class citizen. We talked about this, right? So in software, code is the first-class citizen. In ML, data is first-class. Because if your data changes and is incompatible, your model doesn't work, right? So its data becomes really important. So major becomes change in target or data that is incompatible, okay? Minor is when you improve your model. That means you go from one version to the next type of model and is doing better. That becomes minor. And pipeline is when you basically change the pipeline, how you load and run this, basically this model. So that could, again, this is just one way of versioning it. It's not the standard way for ML models. Now, it's just retrieving the older models, just doesn't have much, but overall ML framework, they might internally version the model, and you can actually see that in MLflow, or whenever if you have a run and if you have those, MLflow creates that metadata, local metadata on your machine. You will see it has versions for the models already. So that's possible. They use some internal mechanism for this versioning, and it's not specifically the version that you use it in your product. So that's also something to keep in mind. Now, we talked about data lineage before, and what we also have something called model lineage. So we want to talk about what's model lineage. So model lineage, you need to keep in mind the model again has code, data, and configuration. And the model lineage basically means that you should be able to say for this version of the model, what was used in it, what code, what data, whose data was used in it, what's the configuration, that becomes the model lineage. Right? Because at the end, remember that, remember as part of data lineage, you actually do model versioning, model control. Why? Because a model technically memorizes the data, right? So if you do a data lineage, the model itself is a mapping for that data from one X to Y. So it has basically information about the data, so it should be part of that. So here you need to keep in mind all the artifacts that you need. And let's bring it here. Then the next thing comes on is going to be your model registry. And model registry is that, well, I have a model, I trained it, and I have everything around it. I have artifacts, metadata, model, parameters. And I want to register this model, that I want to basically tag it for something. staging, production, archived, and again, those could be a standard, but there are different libraries that use different basically registry tagging. You can also add your own tagging. But normally staging is that when you produce something that you think is a good model, but it's not, it's a candidate to be a production model, but it's not yet determined. Like maybe you need to do additional tests. So that's where you register your model as basically staging. But from staging, in order to go to production, you do maybe a series of tests, do a comparison and benchmarking. And then if it's a good model, you move it from a staging to production. And the previous model from production goes to archive, basically. That's kind of like a sequential changes that you introduced. Now, if we